My name is Maria Kolokotroni from Brunel University in London, UK. The title of my presentation is Ventilation and Energy Aspects of Food Retail Buildings, authored by myself, Professor Savastasou, and Dr. Babules Guarisanker from the RC UK Centre for Sustainable Energy Use in the Food Chains at Brunel University. The food chain. This slide presents what we mean, or what it is meant by food chains, from the products, agricultural products, to processing, and then the transport and the consumption of foods, as the strip of photos represents, but also in the square cycle in the middle, it shows that the food chains, and so the energy used by the food chain, is in farm operations, processing, manufacturing and packaging, transport, logistic, retail, food services, establishment, household operations, and also the disposal and recycling, and also the energy that it is used for the import of foods in a specific region in the UK in this case. Our projects, as all these research projects, it is arranged in different work packages, and in our case we've got the horizontal and vertical web work packages. The horizontal ones, they are about food production, distribution, retail and consumption, representing the food chain, and the vertical ones is energy and resources flows, including waste, which is where energy sits as well, and then interactions and integration with UK energy supply systems and socio-economic aspects, and also we have the interactions, dissemination and impacts. The project is funded by the UK Energy Research Council and Manufacturing the Future. It is based at Brunel University with the Director Professor Savastasou, and also Manchester University and University of Birmingham, with a contribution of 36 other organizations from industrial organizations and also departmental and government and dissemination organization. And this is the website of the project. Now, focusing on the topic of this paper, energy use in the food chain, actually there are many figures of how much energy is used by the food chain, and these are expressed in many different units. Some facts I'm presenting here. For example, worldwide, the food energy system, the food system, I should say, is responsible for 33% of the GHG emissions. In the USA 16% of the national energy budget is used by the food chain. In the EU, for industry only, food and tobacco industry is 10% of energy used by the EU 27 industry. In the UK, 18% of total UK final energy use, or 195 megatons of CO2 equivalent. The graph below is about the UK, and it shows how energy is used in the different areas of the food chain, from fertilizers to net trade, which is energy used for imports and so on. And we can see here that retail and catering is where most of the buildings are used to process food, or to for retail of food. It is quite a high percentage of the energy use. In our project, we are not looking at fertilizer or farming and fishing, so we are looking at from factory to the waste. Focusing more on the energy use in food retail and catering, we can see here in the UK that it shows the energy which is used in terawatt hours in this case, rather than CO2 emissions. in all non-domestic buildings, you can see here that retail buildings, which includes all retail buildings and not only food, they consume quite a lot, or they use quite a lot of the energy, and also hotel and catering, which is about catering facilities. And then we have a split up of the different components where this energy is used, but in the next slide I have presented it with a pie chart, again in the UK, where we can see that heating is a high percentage, both in retail and hotel and catering, because it is the UK figures. But cooling and ventilation as well is a high percentage of the energy use, but lighting as well is quite high. Looking at the energy requirements of supermarkets, again, there is quite a lot of data and diverse data in this area. How much it is used, the UK benchmark is about 261 kilowatt hours per sales floor area of fossil fuel and more than 1,000 kilowatt hours of electricity for typical supermarkets, and the range could be between 700 for hypermarkets to 2,000 for convenience stores. In the graph here you can see some figures that they were published recently in Energy Policy, that they shows that the supermarket chains in the UK, they are all reducing their carbon emissions compared to 2007. Only one chain is increasing, but this is because of the expansion of business and not because they are not more energy efficient. Narrowing, focusing more, if we look at supermarkets as well, the electrical energy used in a typical hypermarket in the UK is high in refrigeration, lighting, but also HVAC equipment. And if we look again for the chilled food cabinets, we can see that there is energy loss for lighting, or energy use for lighting, and energy loss through conduction, radiation, and evaporator fans. But infiltration accounts for more than 3/4 of the energy use, and quite a lot of research has been carried out to improve this in refrigerated cabinets. For low carbon supermarkets in the cooling and ventilation, in summary, refrigeration accounts for 30 to 50% of electricity use. Heating, cooling, air for ventilation may require twice the energy of heat loss through conductions through the external envelope that they have been improved a lot during the last year. Envelope infiltration, air tightness tests are mandatory with a maximum or limit in air permeability of 10 cubic meters per hour per square meter at 50 pascals. And if we look at the ventilation strategies, we can divide them into two categories: those integrated with other raw carbon design strategies and others integrated with equipment. There have been a few studies about how we can improve the energy efficiency of supermarkets, and in this one that was published in 2011 by Target Zero, they show the energy used by a base case building, but also different packages with different energy efficient measures. And we can see in package B, which is the more efficient in terms of reductions in total emissions, but also the least capital cost and the most return, that ventilation features quite strongly with specific fan power reduction, with ventilation heat recovery, and with improved air tightness. Also, in another study that again they propose energy efficiency measure, ventilation cooling with catches, roof vents with natural ventilation as proposed, and also controlled by CO2 concentration. Now, as we said, refrigeration is quite high component and quite core in the function of the supermarket, but refrigeration interacts quite a lot with the HVAC system. In this slide, we have got the supermarket energy demand, which is the building there, lighting, preparation, food, services, cabinets, and others. that they have a cooling demand and a heating demand. And we've got the medium temperature and low temperature refrigeration cabinets, and also domestic hot water demand. Usually in the supermarket, these are provided through electricity from the national grid and a standby operator, and this electricity will give the energy to the chiller and the refrigeration that will feed the different demands. In the UK, heating usually is done by gas, so we have gas-fired boilers that they provide the heating demand and domestic hot water. At Brunel, Professor Tasu has carried out with his team quite a lot of work on novel CO2 refrigeration systems that they have been tested extensively in the laboratory and actually with modeling and calibrated from data in installations. In this case, a gas engine based combined heat and power system is proposed, which will provide the electricity that will provide electricity for the different systems in the building, and also electricity for the chiller and the sorption chiller and the volatile DX CO2 refrigeration system. The gas engine also will provide heating for the regeneration of the sorption chiller and directly for domestic hot water, which can also provide some for the heating demand of the building, so making the whole system more energy efficient. This proposed CO2 refrigeration system can achieve 30% energy savings as opposed to the more traditional one. Now, the combination of this CO2 trigeneration systems with ventilation heat recovery is another step that we are investigating, and preliminary results show that by controlling the head pressure of the refrigeration system, a proportion or all the heating demand of the supermarket can be satisfied with heat recovery. So this is one of the areas, I wrote there focus 1, that we are trying to concentrate our research. Focus 2 is the use of phase change materials for thermal storage. In this AIVC conference, we've heard quite a lot about PCMs and how they have been used, and there is a vast amount of research in this area. We have developed a method at Brunel to investigate the impact of active PCM systems in displacement ventilation in large enclosures, and this has been done for airport buildings, but this can be easily applied, or we would like to investigate how it will apply to large supermarket buildings. So the focus is PCM heat exchangers. We've got a displacement diffuser, PCM plates retrofitted, 2 configurations, 8 and 16 millimeter air gaps, and you can see here the temperature range and the physical characteristics of the PCM and the comfort temperature. The study was done with Transis and Fluent. The Transis modeled the HVAC system and the PID control system, and Fluent models the airport airflow. These are coupled together, and the model has been calibrated using laboratory testing. And the developed model has been looking different parameters, and it is indicated that 18% savings, energy savings, can be achieved by 8 millimeter gap PCM heat exchanger with a full night charge. And the next focus of our studies is catering facilities, again trying to see how energy can be saved in buildings such as restaurants, coffee shops, hotel catering, and so on. And also focus 4 is integration of passive measures, natural ventilation, natural lighting, envelope design and the use of reflective materials, and also users' comfort and thermal comfort limits considerations. And all these investigations will be our contribution to the new Annex 62 on ventilative cooling. Thank you.